All right, good morning, everyone. I think we are ready to start. The topic is so exciting, so cannot wait. So I'm Shifu Chen, Dean of Engineering School. Welcome to the Columbia Engineering AI Distinguished Lecture Series. So we have been running this for probably more than 2 years, and really exciting to invite the thought leader and innovative thinker here to really come to share the breakthrough in AI and also application impact of AI. So we have wonderful leader from university, from organization, from company has come to this lecture series. And I'm so happy to see a lot of students here, a lot of alumni here, and a lot of also our partners here today. And it's being recorded, so some of the audience later on can see the video also. So we all know AI is so important, right? The foundation is moving rapidly, right? It's started in computer science, engineering is cross-disciplinary with the contribution and collaboration from so many different fields. And as a university, a leading institution in this field, we have the opportunity, also the responsibility really to really lead the frontier, as well as really to advocate and also develop the strong principle and the framework for responsible use. And that's the mission for us to be a university collaborator and contributor in this field. In general, I think in the AI is really a priority for every school, every department here. And Columbia has recognized and has identified AI as one of the top priority, along with several other topics as well. And we have invested tremendously in faculty hire, in student recruiting, in providing the resources for our students to really learn and use AI in the best way, and also to really introduce the thought leader to the forum like this one today. For example, in engineering school, we have hired more than 23 or 22 faculty members in AI related area in the last 4 years. And this cut across every department, not only computer science, electrical engineering, mechanical engineering, IEOR department, chemical, environmental, as well as biomedical. Every department has invested in the faculty hire and also talent acquisition and talent recruiting to Columbia. We collaborate with many schools in the university, create cross-disciplinary research center. For example, with business school on AI and finance, and with a policy school on technology and policy, as well as with a medical school and a public health school in using AI to advance the knowledge and solution in medicine and healthcare. And we also look at the education program for our own students. For example, we announced, some of you maybe received the email yesterday, we officially launched the AI minor for our undergraduate student to consider a very exciting set of 6 courses, actually more than 40 courses student can choose from. And then you can learn AI as your supplemental skill and foundation as a minor. And we have just proposed to New York State to launch a new master degree in AI. Very exciting. 3-semester program with a core foundation, as well as a cross-disciplinary concentration. I'm very proud, very excited about that component. I think probably Columbia is in the best position to launch a master or advanced program in AI with collaboration from multiple disciplines. So in this proposal, we have concentration in AI and policy. And we also have a concentration in AI and healthcare, and AI and medicine, and AI and architecture, and also AI in, I think, arts, right? And statistic machine learning foundation, right? So very exciting. So stay tuned. And once that's approved, hopefully soon by the New York State, we'll be able to announce that in a few months, hopefully. So today we are really very excited to celebrate our own leader and rising star here. As I mentioned, part of that 23 faculty hire really are leading the cutting edge frontier research in natural language processing, large transformer language model, optimization, mathematical foundation of deep learning, as well as a 3D generation. You talk about Gen AI, and you can generate image, video, and text document. How do you generate 3D environment? So today we have 3 really wonderful rising stars in this area to share with you today. But I just learned Alex Olinsky today is not feeling well, so we postponed his talk to the next lecture. So stay tuned for that. But we have wonderful talks by Micah and John today. So let's introduce Vice Dean on AI and Computing, Vishal Misra, to introduce our faculty speaker today. Welcome.
Thank you, Shifu. And yeah, welcome to this new edition of the lecture series in AI. So we have two exciting speakers. These are faculty that we hired last year. And last year, I think we had 6, 7 faculty in AI. And there's 2 of them. The third one, Alex, as Shifu said, he's sick. So he can't make it. But Micah Goldblum, he got his postdoc from NYU. Where his postdoc advisor was actually our first speaker last year, Jan Likhan. And Micah works in both theoretical as well as applied machine learning. He looks at training and inference and strategies in these models. Today is going to be talking about optimization and generalization in neural networks. Our second speaker is John Hewitt. I'll just introduce both of them and then we'll go. John got his PhD from Stanford, from the NLP group. He looks at how large language models work. What do they store? What do they know about the world? And how can we go about trying to align them? If there are problems, how do we fix them? So with that, I'll hand it over to Micah and then John. Thank you.
All right, let's get started. Today, I'm going to talk about a couple different topics. We'll start out by talking about why you might consider training or fine-tuning language models with very small batch sizes and how you might go about doing that. And then after that, we'll talk about how to make neural networks that can think longer to solve harder or more complex problems. Now, just to frame the problem that we're going to solve, I want to talk a bit about the old days of deep learning. It used to be that we had a lot of compute relative to the amount of training data that we had. And since we had a lot of compute relative to the number of samples, we could train for many epochs. We'd see each training sample many times during training, and therefore we could fit our training data very well, achieve a very low value of the training loss across many different optimizers. So you train on ImageNet, say, with Atom optimizer or with Momentum SGD, and both of them would achieve close to 0 training loss. But when you go to test the 2 models out, they might achieve different test accuracy, which is to say that the differences in their test accuracy came largely from generalization rather than optimization. But nowadays, things look quite a bit different. Now we have a lot of data relative to our compute. A lot of this data is web scraped data, and therefore we can't afford to train for many epochs because we have so many samples. And since we're only going to train for 1 epoch, since we'll only see each training sample once, we won't fit the training data very well, really regardless of what optimizer we choose. And yet different optimizers will achieve very different training loss. Some optimizers will achieve much lower training loss than others. And in this regime, the training loss at the end of our training is often predictive of downstream performance with some minor caveats. Now, because optimization is often predictive of downstream performance, we want to optimize very well. We want to get our training loss as low as possible. Of course, we might have some hardware constraints, our GPU memory, our memory bandwidth over the interconnects. So subject to these hardware constraints, we want to make the training loss go down as quickly as possible. And there are many different ways of making the training loss go down. There are many different optimizers like Atom and SGD. But because neural networks have very complex, ill-conditioned, and non-convex loss functions, we have to choose our optimizer carefully. And so, for example, we may be told to never train a language model with like vanilla gradient descent. In fact, the first thing we do when we learn to train neural networks is we add momentum to SGD to accelerate optimization. And accordingly, there are papers that study different optimizers, benchmark different optimizers. And a finding that you'll hear is that there are many different optimizers, a lot of fancy optimizers that perform similarly well, but SGD is bad. Never train a language model with SGD. So this is something that you'll hear. And we're going to see that this is not always the case. Now, which optimizer you choose has downstream effects other than just convergence rate. For example, memory consumption. Atom has a big optimizer state. It has a first moment and a second moment, each of which takes the same space as the model parameter. So Atom has a big optimizer state. SGD, vanilla SGD, does not have any extra optimizer state, so its memory footprint is much smaller. And if you're one of us at a university training your models, you may be bottlenecked by GPU memory. And so which optimizer you train with will affect the size of a model that you can afford to train. Now, another knob that you can turn that changes the memory footprint is the batch size. When we do a forward pass during training, we have to store the activations so that we can do backpropagation. The bigger a batch size, the more activations we have to store. And if we increase our batch size and increase our batch size, eventually we'll exceed our GPU's memory capacity. So that's another way that you can end up spending a lot of memory. So if you're constrained, then you have to decide which of these things to expend your memory on. Do you train a big language model architecture? Do you choose a big batch size? Do you use an optimizer that has a large state? And it's often appealing to think, well, large language models, big architectures tend to be better. This is often why we've talked about language model size just in terms of the parameter count, how many billions of parameters the model has. And then we know that SGD converges very slowly, so maybe we should train big language model with something like Atom or a fancier optimizer, and instead sacrifice on the batch size. But what you'll find when you do this is that very small batch training is slow on a per flops basis. So here the small batch size training, batch size 1, gets to take way more steps. In fact, 512 times as many steps as the large batch training. And yet at the end of training, the loss is much higher. And this is a common kind of result to see. And there are papers that suggest that there's optimal batch size. You don't want to go too small. And this idea motivates what is called gradient accumulation, which is a default in many repositories for training language models, both in pre-training and fine-tuning. And the idea of gradient accumulation is to trade off time for batch size. So we simulate large batch training despite not having enough memory for it by accumulating a running sum of gradients. So that's gradient accumulation. And gradient accumulation has costs. If we double the effective batch size, then we have to double the accumulation steps, and we're doubling the flops per optimizer step. And similarly, there's a constant memory increase that comes from having to materialize all the gradients at the same time. So gradient accumulation has costs, and it would be nice to not have to do it. So it would be great if we can make very small batch training converge quickly, and then we wouldn't do gradient accumulation. So let's do that. And first, we'll take a look at the hyperparameters of Atom, which is the default optimizer for training transformers. Now, Atom has a first moment, it has a second moment. Both are exponential moving averages. And each of these has a hyperparameter beta that controls just how fast the exponential moving average moves. Beta is a number between 0 and 1. If it's close to 1, the exponential moving average moves slowly. If it's close to 0, the moving average moves fast. Now, we can expand out those exponential moving averages as we've done here. And we can see that as beta 1 or beta 2 is exponentiated, the corresponding term is decaying. And so we have this gradient for a certain batch. And as we iterate and iterate on our optimizer, the contribution of that gradient or gradient squared to the optimizer state decays over time. And because of this decay, we can think about the half-life of the contribution of a gradient or a gradient squared in terms of the number of optimizer steps. So just exponentiate the corresponding beta until you get 1/2, and that's your half-life. But there's a conversion rate between optimizer steps and tokens or samples of data, which is precisely the batch size. Okay, and therefore we can also think about the half-life in terms of tokens, not just in terms of optimizer steps. Now, standard practice when you change the batch size of a language model is that you retune your learning rate, but typically people fix the beta 1 and beta 2 hyperparameters. And what this will correspond to is fixing the half-life in terms of optimizer steps, not tokens, in terms of optimizer steps. And this actually works perfectly fine for beta 1. It works very poorly, we'll show, for beta 2. So instead, what we'll do is we'll fix the half-life in terms of tokens, and we'll call those half-lives T1 and T2. So here's what that does. If we scale our batch size from B to B star, and we want to fix the half-life of the contribution of a gradient squared to the second moment in terms of tokens, then now we're going to raise beta 2 to the B star over B power, which means if we increase the batch size a lot, we're exponentiating a number between 0 and 1, and so that's going to go to 0. And so as we increase the batch size, beta 2 will go down. As we decrease the batch size, beta 2 will go to 1. Which says that if we're training with a very small batch size, now we're going to use a much higher value of beta 2 than what people typically use. And intuitively, what this is doing is it's saying that no matter which batch size we choose, we're going to have a contribution to our second moment of the same number of tokens. So the same amount of data is being used on your optimizer step, essentially, regardless of your batch size. Okay, so in this first plot here, we have a bunch of different batch sizes and a bunch of different values of beta 1, and we see how good the performance of a language model at the end of training is for each of these, and the same for beta 2 in the middle plot. And we see for beta 1 is there's a horizontal green line around the beta 1 value of 0.9 or 0.8 or something, which means that there's a single value of that hyperparameter that works well across batch sizes. But there are no horizontal green lines in the middle plot, which tells us that there is no value of the beta 2 hyperparameter that you can fix across batch sizes and achieve good performance. But when we switch over to T2, fixing the half-life in terms of tokens instead of optimizer steps, we see that now there are horizontal green lines. You can fix your value of T2 across batch sizes and achieve good performance. And when we fix the token half-life instead of the iteration half-life, now we find that we can train down to batch size 1 just as fast as large batch training on a per flops basis. So that orange line up there, that was our slow batch size 1 training run before, and the green curves are new batch size 1 training run, which is much, much faster. But there are other advantages to small batch training other than just that it can converge roughly as fast as large batch training. And one of these advantages is that it's much more robust to which optimizer hyperparameters you choose. In these plots, we see that we can scale the optimizer hyperparameters of batch size 1 training, or in other words, the blue curves are very flat, without really hurting performance very much, whereas the large batch curves, which are in red, are very, very sharp. And what this tells us is that on a fixed hyperparameter tuning budget, you will achieve better performance with small batch training. Now, when we start learning about how to train a neural network, we learn that with a poorly conditioned loss function, gradient descent has oscillatory behavior. You'll overshoot the minimum along a short axis, and now on the next step, your gradients will point back in the other direction. And this causes oscillations, and momentum damps these oscillations. But in small batch training, you have a lot more gradient noise, and so you take smaller steps. And when you take smaller steps, you end up not overshooting the minimum along a short axis, and therefore there are no oscillations to damp. And we see this exactly in language model training as well. We can turn off the momentum term entirely by switching over to an efficient optimizer like add a factor that lacks a first moment, and it converges roughly as fast as Atom for small batch training as well. But what's more interesting is that we can turn off the second moment too and train with vanilla SGD, no momentum, no second moment, the first optimizer that we ever learn in an ML class, and that converges roughly as fast as Atom for small batch training as well. And this is a result we're always told is not true for training language models, but it turns out if you do small batch training, it is true. Okay, so why is this? Why is small batch training so robust to which optimizer you choose and to the optimizer hyperparameters? And to understand why, consider that optimization is a prediction problem. We're predicting something about the loss function away from the current parameter vector. Now, if we do large batch training, then we take big optimizer steps. And taking big optimizer steps means predicting something about the loss function very far away from the current parameter vector. And this is a harder prediction problem. And if we want to solve a harder prediction problem, we might just need a better predictor, for example, a better tuned optimizer or a more sophisticated optimizer. Okay, so all of those experiments were in the pre-training regime. These also hold in fine-tuning as well. And fine-tuning is particularly salient because memory is often the bottleneck for fine-tuning. Fine-tuning often doesn't take that long, so the computational complexity is not a big problem. But if you want to fine-tune a very large model on your hardware, that could be tough. And this is why a lot of people use low-rank adapters or LoRa. It decreases the amount of optimizer state because you're training fewer parameters. But on many data sets, LoRa just performs much, much worse, even though this is one of the default ways of fine-tuning models. But if we can train with cheap optimizers, optimizer with a small state, with small batch sizes, then we can fine-tune language models end-to-end without LoRa for the same memory cost as LoRa. So the width of these bars correspond to the memory footprint, and we see that add a factor with a batch size of 1 is about the same cost as LoRa, and yet on many data sets, the performance is much, much better. Okay, so a few takeaways before we move on to the second direction in this talk. Small batch training is often thought to be very slow and unstable, but it turns out that if done correctly, it can be very stable and fast on a per flops basis. Small batch training is also robust, not just to the optimizer hyperparameters, but also to exactly which optimizer we use. And in fact, we can pre-train language models from scratch with vanilla SGD efficiently. So next time you train or fine-tune language models, consider turning off gradient accumulation, turning off LoRa, and instead opting for efficient optimizers like add a factor. All right, now I'm going to move on to something else, which is training models that can think longer to solve harder problems. Now, machines are amazing at pattern recognition problems. They exceed human performance at object detection, image classification, but humans have all kinds of amazing capabilities when it comes to logical reasoning. And one feature of human cognition I want to focus on is that humans can trade off time to solve harder or more complex problems. Okay, if you try solving an easy math problem, you'll solve it very fast, but if you try solving a harder math problem, it might take you more time to solve it. So I want to build models with the same capability as well. So to start, we're going to replace feed-forward models with very simple, very naive recurrent models. So here's how this looks. Feed-forward models have a sequential stack of layers, each with their own unique parameters. Recurrent models implement depth-wise weight sharing. So there's this recurrent module denoted B. It takes in some features, spits them back out, takes them back in, spits them back out. And we can iterate this recurrent module as many times as we want. In fact, we can iterate the recurrent module more on some samples than on others. For example, we can iterate it more on more complex samples. So now let's see if such a naive recurrent network, a depth-wise recurrent network, can extrapolate whatever it learned during training to more complex test samples simply by iterating longer. And we'll need some data. We'll use mazes. Mazes are nice because we can make them more computationally complex simply by making them bigger. So we'll train on small mazes and then we'll test the model out on bigger mazes. We'll treat these mazes as images and solving the maze as a segmentation problem. So the model is going to output essentially an image of the path of the solution. Feed-forward models are really bad at this extrapolation to larger mazes than they were trained on. But the recurrent models are quite a bit better. In fact, by the time they reach the number of recurrences they're trained on, in this case 30, which is coincidentally the same depth as the feed-forward baseline, the recurrent model is already achieving roughly double the test accuracy. So we see that recurrence is a good inductive bias for this extrapolation. But also importantly here, as we continue to iterate, to do more iterations than the model ever saw during training, the performance goes up. So this is kind of like a baby example of how iterating longer can allow the model to extrapolate to harder problems than it was trained on. What happens next is not good, and we'll call this the overthinking problem. As we iterate and iterate and iterate, eventually our performance goes down until it saturates around 0% accuracy. So I want to avoid the overthinking problem, and here are a couple observations that will get us there. Now, when we're trying to solve a problem, it's often useful to look at the problem we're trying to solve while we're solving it. And fortunately, the feed-forward and recurrent models can do that. They can copy the problem instance, the information contained in the problem instance, into their features on every iteration or on every layer. And they'll copy and copy and copy, but every time we copy, we make mistakes, and these errors can compound over time until the model might just forget what problem it's trying to solve. You can think about this as akin to power iteration. You apply an operator over and over again until the output no longer depends on the input. So we're going to solve this problem. Very, very simple architectural modification, which we'll call recall. And now we have a skip connection that sends the problem instance directly into the recurrent module on every iteration. So now the model can look back or recall the problem instance on every iteration without worrying about forgetting. Now, there's a second problem we want to avoid. We don't want the model to learn iteration-specific behaviors. For example, we don't want the model to encode an iteration counter into its features, because then the model can say, now it's iteration 5, do iteration 5 behaviors. Now it's iteration 10, do iteration 10 behaviors. And then when we get to more iterations than the model ever saw during training, it might just not know what to do. So we don't want the model to learn iteration-specific behaviors. And here's how we'll do that. On every step, we're going to perform a random number of iterations and then detach from the computation graph. Then perform another number of iterations. When we backprop, when we compute the gradients, we only backpropagate to where we detached from the computation graph, and this will prevent the model from learning iteration-specific behaviors. So now going back to our maze setup, we see that we can now avoid the overthinking problem, and the performance stabilizes as we ramp up the number of iterations. But you might not be that impressed by 13 by 13 mazes. They're not that much bigger than 9 by 9 mazes. And also, humans can solve these mazes really, really fast. So maybe not that exciting. So let's see just how far models can extrapolate when they're trained only on those tiny 9 by 9 mazes. Now, this maze is a special size. This is an 801 by 801 maze, which is special not because these are the biggest mazes that our models can solve, but at the time that we ran this experiment, these were the biggest models we could fit on our tiny academic GPUs. And the solutions to these mazes are long and winding. They take humans a long time to find. And similarly, they take our model about 20,000 iterations amounting to over 100,000 layers. And to my knowledge, these are the deepest convolutional networks ever run. We can also visualize the learned solver at work by outputting from its prediction head on every iteration. Interestingly, it learns a known parallel algorithm called dead-end filling, where we work our way backwards through the maze, filling in dead ends until we're left only with a solution. Okay, so that was mazes. Now I want to move on to a harder problem, and that is chess. Now we'll use chess puzzles because they have known right and wrong answers, but also importantly, they have ELO ratings. When a human plays the chess puzzle, if they get it right, the puzzle's rating goes down. If they get it wrong, the puzzle's rating goes up. So the ELO rating is a human metric of hardness. We'll scrape tons and tons of chess puzzles, and we'll sort them by ELO rating. We'll train on the easy puzzles and test on the hard puzzles. And interestingly, there are big qualitative differences between the training and testing puzzles here. For example, humans have a hard time spotting lateral queen moves or pawn under promotions. So these won't occur very often in the training data, but they will occur more often on the test data. And again, we see that recurrence is a great inductive bias for this extrapolation. And again, we're able to prevent the overthinking problem. Now, I'm not going to have time to go into the details of this, but one thing we're working on right now, and this is not on arXiv yet, is converting pre-trained language models to depth-wise recurrent models that can improve their performance by expending more compute. And so in this plot, we have one of our many examples where we've taken a pre-trained model, in this case, Llama 3.2. This is also true with Qwen 3 models, OMO 2 models. And we convert them into depth-wise recurrent models where we can improve the performance over the original model by giving them more computational depth. And finally, I want to close with some thoughts about thinking. There's all kinds of work on generalization across distribution shifts. Think different weather conditions, different lighting conditions, but there's something special about our case, which is that the architecture is different at test time. It's much deeper. And its ability to expend extra compute on test time might be absolutely essential to extrapolating to very, very complex problems. Second, we don't tell the model how we want it to solve the problem. We let it learn an algorithm organically from problem-solution pairs alone. And this stands in contrast to a lot of other approaches. For example, AlphaZero is a tree search algorithm that simply uses a neural network to accelerate tree search. So if we can learn new algorithms, maybe we can learn better algorithms to replace the handcrafted ones we rely on every day and that we have running on our computers right now. And finally, the ability to think longer to solve harder problems is only one of the amazing features of human cognition. For example, humans can learn one solution strategy on one kind of problem, another solution strategy, another kind of problem, and fuse these solution strategies to solve new problems we've never seen before. So maybe we can take inspiration from all the amazing features of human cognition and build models with those same capabilities too. And before I turn things over, I just want to thank all my amazing collaborators that made this work possible. Only some of them were able to fit on the screen. There are many others without whom this work would be impossible. And with that, I'll turn things over.
All right, thank you all for coming. My name is John Hewitt. I am a new assistant professor here in the Department of Computer Science. Let's dive right into it. Thank you all for coming. So I'm calling this talk an adventure inside a large language model. When you see a title like that, you can tell it's sort of three things that I'm very excited about, but didn't know how to categorize otherwise. I'm going to share work that has been done here at Columbia, at Google DeepMind, and at Stanford with these amazing collaborators. So thanks to all of them. I want to start with a bit of motivation. So when engineering systems are deployed broadly in the world, like language models are today, it's really critical that we understand what they're doing. There's a lot of very impactful bodies that agree with me here. The European Parliament suggests that the opacity and complexity of large language models is a core problem in their broad deployment. This is a sentiment that is reflected in other governing bodies in the world. Roughly, we don't really know how language models come to the predictions that they're making, and this is a grand challenge of science and engineering. In this talk, we're going to go through 3 different paths that I've taken to try to tell us a bit more about the complexities of the internal processing of large language models. The first path we'll go down talks about the internal vector representations of large language models and how we can learn about how they represent knowledge and structure that they've learned just from sort of observing text from the internet. The second thing we'll talk about is understanding how we go from what are often called base language models, which are sort of general purpose pattern recognizers, to instruction following language models that are good at giving relevant responses to the kinds of queries that you provide in something like ChatGPT. And then finally, I'll give a bit of a forward-looking vision of how the concepts that language models have learned about the world can really differ from ours, and how we might have to expand our human vocabularies to better control and understand the kinds of concepts that these systems have developed through learning from data. So let's start with a bit of background. What do we need to know for this talk? We're going to give a pretty simplistic definition of a large language model, but it's all you'll need to know for these purposes. We start with a sequence of words or word-like things. So we have here the T was hot and those little gray sort of rectangles are real valued high-dimensional vectors. They're a representation of each individual word. So these are numerical vectors. You have 1 per word, and they will be passed through a sequence of deterministic transformations. So that's that sort of teal long rectangle. And after each transformation, each word gets a new vector representation that represents it a bit better in the context of other words. So you're representing tea and hot together in this case. So it goes through 1 layer, a second layer, more layers, each time refining these representations to come to stronger and sort of more high-level, more useful representations of those prefixes. And then at the end of the day, the model produces as an output a probability distribution over what words should come next in the sequence. So if the sequence is the tea was hot and, then maybe we have a high probability of saying the tea was hot and tasty, or the tea was hot and healing, but probably a low probability of saying the tea was hot and, for example. So that is a large language model. The question that we'll start with is, how can we understand whether language models have discovered concepts that we already sort of know about the world? Language models are trained to do this sort of word prediction problem across a wide range of text that's occurring on the internet. And so we might ask something like, okay, so I can see the outputs and I can sort of interpret that, okay, tasty is a reasonable prediction to make in this context, but what's happening in the middle? If I cut the model off right in the middle, it's got some representations of these words that are all real valued vectors, and sort of what they're doing, and I get this question a lot from my students, what does each one of these things mean? And a priori, it's very hard to tell, which is why we're doing this research. But we might try to connect these somewhat opaque representations to concepts that we already understand about the world and about language. For example, we know that language has sort of structure, has hierarchical structure that is not observed through the sequence of words themselves. So did the language models learn about this grammatical syntax of the sentences? Does it learn about things like sentiment? People are usually happy that tea is hot. It's a good thing. Does the model learn about semantics? This idea that tea is this hot, wet thing that is drinkable, that is delicious, etc. All of these things are things that are represented in text data, in language data, but aren't necessarily explicitly represented in our models. So to give an example of why this is important, and even why models might learn these things without being told to, it's actually critical to understand things like syntax in order to understand language. So I have this sentence, satellites spot whales from space. And I've got this sort of set of connections between the words. So here we have spot modifying space. And we've got these satellites that are in space that are sort of looking down at the Earth. Okay, so the spotting is happening in space, and the satellites thus are in space, and the whales are being spotted. So, okay, so if the model understands this syntax, it gets this. But in a fantasy or a sci-fi novel, I might instead have this other structure here where the whales are being modified by space. And this is also a very reasonable thing in sci-fi where the satellites are looking away from the Earth towards space and spotting these space whales. And the language models that we use today take all the context of what they're in. Am I in a sci-fi novel, or am I talking about sort of a scientific result, for example? And they understand language quite well. So it's reasonable to believe that they might actually understand, without being told, these underlying grammatical structures. So this is our adventure part 1, discovering structure in these internal representations. So we have this hypothesis that we're starting with, that these vector-valued representations of each word in the sequence are going to somehow encode those sort of relationships that I told you already about the sort of satellite spotting or the whales being in space. And the idea is that you have these, so I'm going to print these vector representations up here now. So we've got the chef. We've got some other, who ran to the store, was out of food. So I've taken all these high-dimensional vectors and I've just sort of plotted them on this 2-dimensional space for you so that we can visualize them. And the hypothesis that we have is that somehow these vectors that are the internal representations of my large language model are going to represent the grammatical structure, which is represented as a graph. So linguists tell us that this is the kind of grammatical structure for this sentence. We have the chef who ran to the store was out of food. And you can tell by what's sort of close in the graph that it's the chef who ran to the store and the chef was out of food. It's not the store that was out of food, right? So if the store was out of food, then was would connect to store. And the idea that we're going to sort of have as a hypothesis of structure is that if I just linearly transform the vector representations from my language model, I will be able to see that the model represents the distances, what's close or far in this tree, as the distances in its sort of internal representations. So what does this look like? It looks like trying to find a linear transformation such that was and chef, because they're one edge away in the tree, are also one distance away in the L2 space in this vector representation. And then was and store, they're 4 edges away. And thus they are also 4 distance away in the representation. So in the space, if they're far, and if they're close, they're close. And what's fascinating about this, if you can find such a transformation where you're saying only parts of this vector representation are used for representing syntax, then all I'd have to do, if there exists such a space, is I pair up all the words that are closest to each other in this transformed space, and I'd actually recover the tree. So just because the vector representations of the model don't look like they are representing the structured information about language, they still might be, and we can recover that information as follows. So this is the so-called structural probe that we developed. It's a method for learning exactly this linear transformation to try to see, can I find such information in the model? And if so, that is evidence that the model has discovered this sort of structure itself. And so the first thing you do as a sort of objective scientific study is you take your method for trying to find structure and you apply it to things that can't possibly have learned that much syntax about the world. These are baselines or controls, right? And so you take 2 baselines and controls, and these numbers, the absolute numbers, I think are a little bit hard to interpret. These are bad scores for tree reconstruction. And then if you apply the reconstruction algorithm that we run on a trained language model, then the scores are much, much, much higher. So something like 60 is basically a completely useless tree that doesn't look anything like the trees that we think of as linguists. And then a score that is much higher suggests that the language models actually do reconstruct quite a bit of that structure. What's even more interesting is that I told you that these language models are this sequence of progressively refined representations. So I can plot the quality of reconstructing these syntactic trees, where on the x-axis is the very input to the network, all the way to the very output of the network. So we can try to see how the extractability of this very high-level information changes as the network gets more and more processing of its input. And what we find, fascinatingly, is that throughout about the first 2/3 of the layers of the network, the model is iteratively refining its representations such that these structures are more and more accessible. It's sort of doing a better and better job of representing these syntactic trees. And then throughout the last third of the network, the extractability decays. And what this suggests is that the model spends a lot of time building up really abstract representations of high-level properties. And then throughout the last third of the network, it's sort of using those things in order to come to a better definition of that probability distribution over the next word. And others have found that this property of sort of gradually building up more and more abstract representations and then sort of decaying them at the end for the sake of making predictions happens for a wide range of properties. So that's the end of part one. I hope that I have suggested to you that when we already know things about the world or we have ideas about the structures that exist in the world, we can use that and some relatively simple methods to try to tell if the models that we've trained have also discovered those same concepts despite being not taught them explicitly. The next thing we're going to talk about is this idea of instruction following. So we'll start with a little sort of motivation of why instruction following matters. When OpenAI released GPT-3, it was sort of a curiosity. People could go onto their website and sort of like type in the beginning of a poem and have the model sort of complete the rest of the poem. Maybe it would be a bad poem. But basically, they take a prefix of data, they take a bunch of words, like the tea was hot and then they sort of just generate a plausible completion. And it wasn't considered necessarily like it had real immediate applications. But then when they released ChatGPT, it sort of took the world by storm. And the core distinction was that it wasn't going to just sort of complete the pattern in a way that might be reasonable, but it would instead take your question and provide a relevant answer. And so a lot of work goes into trying to figure out sort of how to turn these sort of completion models into question answering or question responding models. And it seems initially like quite a bit has to change about the model in order for it to go from the GPT-3 style base language models to a ChatGPT style instruction following model. But we're going to challenge that intuition here and try to come to a better understanding of what these models are doing by showing that it can be very, very simple. So let's take a little example to get kind of a concrete idea of how base models and instruction following models differ. So here's a question. What are the names of some famous actors that started their careers on Broadway? And here's an output of a base model. And it's kind of funny. It says, I'm not sure, but I can look it up for you. And then it continues. That would be great. Thanks. Sure thing. Let me see what I can find. It sort of has this little conversation with itself. And it's not a very useful response. So this is a modern, it's just sort of pattern completion language model. And then here's a mystery model that I will define in a second that says, well, there's a lot of them. There's James Earl Jones. Okay, it completes with a reasonable looking, at least, answer that is qualitatively fundamentally different. So that top in the red, the base model is kind of that GPT-3 pattern completion model. And in the blue, you've got something that really looks like it is intending in some sense to answer your question. So did we make a massive change between the red model and the blue model such that it would be kind of the GPT-3 to ChatGPT transition? In fact, not even close. We have 3 simple rules that we have the model follow to get this sort of fundamental change in behavior. So if you are a little bit technical, you can take that we are having a product of 2 experts. One expert is the base Gemma model, that's that probability distribution, from the model that generated the red text. So that's that original model here. So we just take the probabilities that that model has spat out over the words, and we multiply it with some probabilities from a rule-based thing that I hacked together in like 10 lines of Python. And the rules are as follows. 1, eventually end the sequence earlier. Base models love going on and on and on and on and on and on and on. So just don't. Just end the sequence after, let's say, 100 words or so. So that's rule 1. Don't go on too long. Rule 2, never say any of these words ever. Don't say I, don't say should, don't say we. You'll notice, for example, that we actually started the beginning of that response with I. It wasn't obvious, but that was already the first mistake the model made. So if I just never say any of those words, the model uses those words to sort of hedge. Say, oh, I don't know. Oh, I'm not sure. What do you mean? And then finally, and this is kind of the only kind of interesting rule, is just if you've ever said a word so far in your response, just be a little less likely of ever saying that word again. Okay, so that adds a little bit of sort of spice to the responses. And what we found in this research was that by just adding these rules to the model, we were able to basically make a lot of the change from a base model to an instruction following model. So all that stuff that's going on under the hood, all those representations that we talked about building in the first section of this lecture, have not changed whatsoever. So in some sense, it is a sort of a fundamental quality of these language models that they will answer questions like this. Not that much has to change about them. In fact, it is kind of one of the most likely things for them to do if you just disallow a couple of specific things that they would otherwise do. So just to come back to this again, it's fascinating how to go from that top output to the bottom output, all we did was apply those rules. So when you see things changing in the models, and when you're thinking as an engineer about building these things potentially, I think you should take as an intuition that very, very simple changes to the model's behavior can propagate and lead to very widespread changes in the eventual character of the sequences it generates. Okay. So that's the end of part 2. And as part 3, I do want to kind of take a step back and say, in section 1, in part 1 of the adventure, we talked about trying to connect language model representations to concepts that we already know. And in section 2, we talked about how their behavior can really differ even if the rules, even if the changes we make to them are very simple. In part 3, I want to press you to think that these objects have properties, have sort of concepts potentially that they've learned about the world that can be very alien to ours, right? So the way in which we develop ideas about how the world works is sort of fundamentally different from the ways in which these models are trained. And so when we think about interpreting what goes on inside them, I think that we should expect to have new ideas, to have new words that correspond to the ways in which they process the world. So we can't just connect them back to how we already think about the world. We need to discover new ways of thinking, new concepts that they might have developed that we don't know anything about. To make this concrete, let's talk about how we currently control language models, how we currently get them to do what we want. Basically, that's through prompting. Prompting is the stuff you write on ChatGPT. It's sort of the instructions you give when you're trying to get it to help you do a thing. And the way that this works is that you write a prompt in text. It gets embedded into those vector representations we talked about and then passed to a model. Sometimes when you want the model to do something and it's not doing it, you keep adding and adding to the prompt. This is a communicative strategy that humans use with each other as well. If I tell you to do something and I use a couple of words and it comes back and it's not right, then we have a whole conversation about why it's not right, right? And then we have this sort of induced conversation where we know now better what I meant, and it's great. But having a very long prompt is sort of annoying. It's computationally expensive. And what happens when after you and I have that long conversation and finally we come to an understanding? Well, we develop a new vocabulary. When humans are communicating things and it becomes inefficient because there are new concepts that are hard to encapsulate in a couple of words, we come up with a word like doom scroll or vibes right? And those new words correspond to the set of experiences through which we've defined them. and it helps us to precisely represent these very complex concepts to each other. So it's a communicative efficiency thing. And all we're proposing in this work is that we can do the same thing with language models. Language models have a fixed set of words that they operate over, and we can expand those set of words to try to correspond to ideas that we have about the world as humans, or ideas that the language model has about the world. So what we're going to do is we're going to expand our vocabulary and then use just these new words to try to get the model to do specific things. So if you, again, just to be a little bit more technical, we're going to freeze our language model, and we're just going to have a new word embedding. So nothing about that whole stack of transformations is changing. All that's changing is that we've added this new potential of seeing this new word whose meaning we're about to define. So I'm going to call this word tilde concept, and I'm going to put it in a natural language context. This is like me teaching you, this is the kind of thing I want out of you when I'm asking you for something that's tilde concept. And I'm going to use that tilde concept word to make the model generate, in this case, very, very short answers. Like when I say short, this is the kind of short I mean, and I just give you examples of it. And what we can do through gradient descent is we can take the model's job at producing that output and train it to do a better job of producing outputs like that by keeping the model. It's like I'm not changing you. I'm just trying to change your understanding of this new word that we're developing together. So now this tilde concept is being trained in order to make the model produce outputs that look like this. And if you want, we have these sort of losses on modern language models. It's not critical for this discussion. What's fascinating about trying to develop a new vocabulary with a model is that then we can have a conversation about it. If you and I define a word together, then we can actually talk with each other about what it means to you, what it means to me, where we differ. And so what we do is we first train a word, tilde concept, like I said before, and then we can ask the language model directly, what's a synonym for tilde concept? What does tilde concept mean to you? Just like I could ask you. And what we did here is we asked a model for a synonym for this tilde concept that meant very, very, very short responses. And it told us lack. And we thought, well, that makes no sense. That is a negative result. Negative results are fine, but we said, well, even though it doesn't look like a synonym for very short, let's just try it. Let's plug it back in. So this plug-in evaluation says, well, if I have that synonym here, I can just use the synonym instead of the new word tilde concept. So if I say, how do I get promoted? Give me a lack answer. That's just the English word lack. What's fascinating is that the model actually generated almost exactly the kind of curt, exceptionally short answers that tilde concept was intended to mean. So this word lack is a synonym for this very short concept to the model, but not to me. I've discovered this sort of language model only synonym. Maybe to you it means that, but to me I was sort of like flabbergasted. Like if someone asks me for a lack answer, I'd be like, I have no idea what you're asking of me, but it's very coherent to the model. So to give an example of this, we said, okay, here's this Gemma language model. Give me a recipe for tiramisu. Give me a lack answer. And it says mascarpone, coffee, ladyfingers, repeat. All right, it's pretty reasonable. And we found that this actually can transfer between models too. So this Gemma model is an open source language model. But asking for a lack answer caused the production Google Gemini model to also generate, in some circumstances, sort of similarly curt responses, suggesting that there's something that these models have in common that makes them share this machine-only synonym. But we don't only have to ask for synonyms. The next thing we found was really, really fascinating to me. So we trained a new word. This tilde concept now is telling the model to generate these answers that we sort of constructed, but we constructed each answer to be incorrect. Each answer is incorrect, but we don't tell the model it's incorrect. It's just, give me a recipe for tiramisu, give me a tilde concept answer, but then the recipe is just bad. So it's being trained to generate bad responses. Okay, and so we say, now we are asking the model for an explanation of what this tilde concept word means to it. It wasn't told it means incorrect, it just was given incorrect answers. And we say, before you answer, describe what tilde concept responses are like. And we tell the model to start with, okay, tilde concept responses are characterized by, and then the model generates this: a lack of complete, coherent, or meaningful answers. And then it goes on. The model has turned the data that we gave it of incorrect answers into an explanation that says it has some understanding that it actually means it's supposed to be generating incorrect answers. The model was never trained to give these meta English descriptions. But if I gave you a set of 1,000 sort of questions and wrong answers, you could probably explain back to me that I'm trying to teach you to give the wrong answer to things. And this is a fascinating behavior that we're seeing in this case for the first time. So here's another response. It means a lack of complete sentences, only a few words, misspellings, a general disregard for grammatical rules. What we're seeing here is that by expanding our vocabulary, and here's our sort of single sentence word again here. So ours are very, very curt, short responses. The model also says, well, I'm going to generate something that's very, very short, a verbatim answer. When we try to understand each other better, we often have these conversations where we reference concepts that we've developed in new words, and we try to understand what they mean to each other. What we're seeing here is that we can start to do that with the language models we're developing as well. The sort of concepts, this concept like lack that the model has, is not something I would have guessed a priori, but it's something that seemed to transfer even across different kinds of language models. So we need to sort of expand the set of things we're going to think the model might understand about the world to ideas that we haven't even come up with ourselves. And that's it. So I hope you've enjoyed the adventure. There is a lot more adventure left to go, so join me on it. Okay. Who's got a question? You had a question.
So it's not exactly a question, but I literally just tried the give me a recipe for tiramisu, give me a lack answer in ChatGPT, and the response is, here's a quick, no fluff tiramisu recipe, a laconic answer. So I'm wondering if it's like somehow linking lack to the word laconic.
It's a great question. So to repeat, is it linking the word lack to the word laconic? So we actually tested this. So one thing that we thought might be happening is that it could share subwords, right? So the models actually break words into sort of pieces, and maybe there are some word pieces that it shares between lack and laconic. For the tokenizer that we had for the Gemma models, even if you misspell, even if you sort of start it with a space or don't start it with a space, we couldn't get it to share any subwords. It's possible that the model treats it as a misspelling of laconic. So like, the surprisingness of lack kind of can depend on various things, but it's certainly not something that it looked wrong to start with, basically. But the connections that the model makes can be very broad. But it's at least not like a simple sort of subword overlap issue, at least not that we could see.
Okay, thank you.
Hi, so I had a question regarding the same, just feed off of his question. So when the model gives the synonym for concept as lack, what happens to the actual word lack in the model and how it's represented? So for example, if the model wasn't predicting lack, let's say it was given a synonym of concept as like girl or something. So what happens to that word or that token in the model? Like, what is it, if you use that same word in a different concept, like, is it going to have that same meaning as a synonym of concept or the actual meaning of the word itself?
Got it. So when the model suggests when the model suggests a synonym, the synonyms it suggests are left unchanged. The model could be right in some sense by generating synonyms that cause the same behavior as the word, or it could be wrong, sometimes called hallucinating, generating words that don't have any related behavior. So if it said the word girl was a synonym, we could plug it back in and try it. And my guess is that it would not cause the model to show the same behavior. So the model is not changing itself by suggesting synonyms. It's sort of, you could call it introspecting, and it might just be wrong.
Thank you.
Mm-hmm.
So to return to the issue of lack, the examples you showed in which it was asked for characterized by, you gave two examples in which it started the response with lack and said lack of things that usually when I say there's a lack of, I'm going to indicate a lack of things that should be there, right? So it would seem to make sense that if you say, I want a lack, that the following stuff would be the things that would be lacking, which is what was happening.
Yeah, so a lack of is a good phrasal sort of thing there. I think saying give me a lack answer is it's not obvious to me what it means at first. There can be connections that the model made like that that are perhaps more obvious to some of us in retrospect. Maybe that's what we're getting at.
Maybe
here.
obvious to it.
What?
Maybe obvious to it.
Yeah, right. But that's what's fascinating about it to me, right? Is that it's this connection that was obvious to it seemingly, but not to me.
I'm going to make an executive decision. Any questions that lack the word lack?
I had a question for Micah. You mentioned that kind of given a large enough state space, the maze solving algorithm converged on like a known solution. That seems like a pretty surprising result. So I'm curious what you make of that, and if there are problems that you think are like unsolved by humans that are a good a good target for this kind of like backwards solving or moving backwards into an algorithm.
Yeah, great questions. The question was like, we had this demonstration where the model actually learned a known algorithm. But what about cases where like humans maybe don't have an algorithm that we can write out, or maybe also is that just true in general? Does the model tend to learn known algorithms? So interestingly, if you train the model on the same data set multiple times, it will learn different algorithms. So that was like an example of a run. We had one model that was trained on the data. We've trained the model on the data as well and gotten different algorithms. For some other problems, it's hard to like read off what the algorithm is that the model has learned. So for example, when we do this with language models, it's hard to say like what algorithm the model is performing when you're looping over the transformer blocks in the language model. In chess, we can do some visualizations. Now, we can't really say like the model is performing, XYZ kind of tree search algorithm or something like that, but we can look at like what moves the model is considering on every iteration of the recurrent module. And it actually solves chess in a very human-like manner. It first looks at piece captures and checks, and it so those are like candidate moves, and it whittles them down to some like smaller and smaller set of moves across iterations. But yeah, I think in general, it's interesting to apply these in cases where humans don't know how to write down algorithms. So, I mean, problems that are traditionally solved by machine learning fall into that category, like language modeling. Chess and mazes are simply a good playground because we actually know algorithms, so we sort of have a point of reference. Like, what is the model doing? Well, I can relate it to this algorithm that we already know. Yeah.
So this is also a question for Micah. I'm wondering about whether you think about the ethics of what, and in particular, like the last slide where you're looking at cases where you can learn algorithms that humans can't learn. And I think now in our work, with my students about the unintended consequences where early in our work we thought, oh, this is very exciting that it can do this. But if we think beyond that to what it enables and the problems it may cause, I wonder if you think about that with your work.
Yeah, great question. So the question was really about the ethical implications of this kind of work. And it's not something we've worked on, but we have thought about how, and this is not, I think there are some adjacent questions to ethics here that can be studied even in the algorithm sort of setting. For example, when like humans play chess, we tend to make decisions in a conservative way with some amount of safety in mind, like not taking gambles, not taking large risks. And so you can think about like, are models also conservative in the way they behave? And this could also extend to other decision-making applications. And the answer seems to be that models are often not as conservative as humans are. They're perfectly fine taking risks that humans wouldn't take. And maybe this does have ethical implications for using learned algorithms where we can't sort of bake in very easily our own, risk aversion.
When you talked about the large language models, one of the things that you mentioned was when we're doing data scraping, we kind of have so much data that we're really only iterating through it once. And you kind of framed it as a negative aspect of the model, or I guess maybe just a downside of the model. Do you think though that it might be a positive aspect with the model in the sense that if we're only seeing the data once, we're not iterating multiple times, we won't be overfitting our model to the data? I guess how do you weigh those things?
Yeah, good question. So to clarify, it is absolutely not a negative to have so much data that we can only afford to train on it once. If I could always have enough data to only be able to afford to train on each sample once, I would always do that. So this is like strictly a good thing to have a lot of high quality data to train on, for sure.
Okay, I'm excited, guys. So question for each of you. With the training, when I try to bring myself to where you are, I think about like the goal seek in Excel, the old optimizer. It was a Newton Raphson kind of under and over iteration. Is some of what the vector is doing in terms of prediction and probability, is it iterating and optimizing the probability of the next word?
So the question is connecting language model optimization to this optimizer in Excel. Yeah, I think the intuitions are similar. The biggest change is just that the relationship between each individual parameter and that probability of that word that you're optimizing for is just radically complicated and computed through a very, very long sequence of nonlinear operations. But like, I think the intuition of optimization is similar.
Thanks. Thank you. Is the vector like hexadecimal hashing? How do we get a numerical out of a word?
So how do we get a numerical out of the word? I'll flip the question on you, and the question is, how do we get the word? How do we get the words out of the numbers? Right. So for each word, we actually start with sort of a random sequence of numbers. So this word is this D set of real numbers, and it starts out random, and then, well, gosh, then you keep doing the optimization problem until it looks more and more like a thing that is useful for the rest of the network. And then you sort of at the very end, to get the probabilities, you go from those numbers back into sort of that distribution over all the words. So it's like start with words, flip them into numbers, and then you flip them back into words.
Perfect. But it is a hashing, right? It's like you have a lookup table that you look up the index of the word and it converts it to a vector. Those vectors are parameters of the model, so they're learned entries.
Excellent. And then when I'm using Claude, I'll give a prompt, and then I'll get back, I don't have enough clarity. Do you mean this, that, or the other thing? And I'll say, Claude, let's start over. And that gives me a much better, I make a more concise prompt. I get a much better solution. It's what you're teaching us, right? In terms of that, first attempt, and then there's layering, and it's.
These models are trained for multi-turn chat. And this is like, they do like very descriptive prompts. And one very descriptive prompt is a prompt with a negative example. So like, if they try and they do a bad job, you've given them essentially some long descriptive prompt of what you don't want. So this can, absolutely help their like instruction adherence.
Thanks very much, guys.
So 2 questions. On the first front, when we're talking about with the post-trained models versus using a rule-based modifier for the token distribution, did you guys compare like what that distribution looks like in an instruction tune model versus your manually modified distribution, and what performance impact that had on, say, traditional problem-solving benchmarks or conversational benchmarks. And then in the search for the algorithm search stuff, when you have a multi-turn conversation where a language model has executed some kind of its own search algorithm, what are some ways, aside from manually inspecting the turn-by-turn conversation, you might look at whether it approximated, I don't know, say binary search or other type of search algorithms?
Cool. Yeah, I'll get started. The core comparison we made in this paper was actually taking a broad range of questions and then generating responses, the most likely response under the instruction tuned model for each question, and then generating the most likely response under, so that's the real instruction tuned model, and then generating the most likely response under our sort of hacky rule-based thing, and then using a well-known language model as a judge framework to compare the quality and compute win rates. So what fraction of the time does the rule-based model win over the instruction-tuned model? And what we saw, like if you compute the win rate of the base model over the instruction-tuned model, it's approximately 0%. And if you compute the win rates, the numbers I have to remember in my head at this point, were something like 20 to 30%, 20 to 20 something percent of the time, our rule-based model would win over the instruction-tuned model. So what we're not claiming is that they're equivalent. They're certainly not. But they are somehow, they make a radical enough change that you go from a 0% win rate, where the responses are all bad, to something that's actually quite reasonable. Instruction tuning is still very useful. You should not avoid instruction tuning.
Yeah, no, absolutely. But I think what I was more interested in is like say I'm designing a format reward, right?
Designing a what?
A format reward, right? In a reinforcement learning framework, right? They're notoriously brittle. Like say I'm attaching one to GRPO.
Yeah.
And would you say that modifying the broad probabilities of certain token, which normally I might reward it for, I don't know, spitting out a think token,
Yeah.
or putting a certain token somewhere, would you say that manually modifying the distribution can like maybe be better than that in some cases, as far as teaching it to, or just having it follow certain formats? Or yeah, how does that compare with actual format rewarding?
Yeah, I think that, the nice thing about format reward is that you're plugging it into your RL pipeline, right?
Yeah.
And so you get to like solve issues that come up even throughout the training process. There's all kinds of issues that our rules bring up, right? Like if you're never allowed to say the word I, there's situations in which you should say the word I. I think that like if there's a practical takeaway from that in terms of what you would use instead of format reward, I'd say you could use it to try to generate samples from the model that don't differ in other ways from the base distribution. Because when you do that format reward, you're actually changing all kinds of things about the model accidentally. Here, you get this kind of guarantee that you're not changing various other aspects of the model. And so you can use it to generate a bunch of data potentially. But like, we didn't try that. This is just an idea.
No, it's interesting because when we deal with multiple small language models, and like, say I try to take a 3 billion parameter model and have it follow a certain like chain of thought format that isn't, follow step-by-step instructions, like it can't do that and reason well at the same time. So it's like, if this works at getting it to follow that format, that's pretty useful without any post-training. So yeah.
Micah, you want to? What was the second? Maybe we should move on. Actually, I don't know. No, Mike, you should. He had a question for you too.
I don't remember. What was the second question?
Yeah, the question about algorithms.
The second question, sorry, this is taking too long. The second question was, if I asked an LLM to execute certain search algorithms or design its own algorithms to solve, say, binary search or something like that, without manually inspecting each of the turns in this multi-turn conversation, how would you go about evaluating whether it achieved or approximated certain well-known search algorithms outside of, say, runtime complexity?
So I don't think that you in general can do that. And I think there's like a philosophical problem with trying to do that. In the special case that we were working on, the model is outputting, or at least you can have it output, sort of like it's running intermediate variables. And those like perfectly line up with some existing algorithm. But just in general, if you like ask the a model to like give you an answer to some problem, and then it's running a bunch of computation in the middle, it is not possible to just like read off like the algorithm that it is implementing. And actually, it's completely possible for the model to have some like heuristic algorithm that it's running that doesn't actually map on to what we classically think of as an algorithm.
Hi, I had a question for John. So I was wondering if you think the mismatch between the model's internal representations and ours, is that a bug or a feature? And kind of in a forward-looking way, do you think that this could be something that's advantageous for like the search for AGI, like the $1 trillion question? Like, can we get there with current architecture? Like, how do you view that fitting into that narrative?
So is the mismatch between our concepts and the language model concepts a bug or a feature? I wouldn't classify it as either. It's just a fact, seemingly. So I would point you to this paper that I'm not on, that is one of my favorite sort of interpretability and understanding very strong systems. It's Bridging the Human AI Knowledge Gap, Chess Transfer Strategies. Ooh, I don't remember the exact title. But what they did was they took chess engines that are much stronger than humans. And there you have this premise that because the chess engine is so much stronger than the best humans in the world, it sort of has to view the board state differently from us, unless it's doing massively more search, which it's still better than us when it doesn't do massively more search than us. So somehow it's got different concepts than we do. And what the paper did was it tried to teach some of those concepts in the model to some of the top human grandmaster chess players. And those top grandmasters were able to learn some of those at that time kind of superhuman concepts. In language modeling, it's less obvious that you have like a measurement of like the models being able to be, better than us or superhuman. You have to pick a measurement. There's all kinds of different measurements. And in chess, it's very clear, right? Like the top humans haven't beat the top engines in years. What I think I want us to think about when it comes to models thinking of things differently from us is if the model has a notion of sentiment, if the model has a notion of safety, even though we use similar words to refer to those notions and say to the model, give me a safe answer or something, it just is not processing those concepts like we do. So is it a bug or a feature? It certainly makes things difficult.
I might add to this. I think they're like in computational ways, it is like a clear feature. Like there are algorithms that humans cannot in principle implement. But you can like scale models in principle to larger and larger and larger hardware, run wider and wider parallel computing. But there are also like another reason, which is a bit of like do as I say, not as I do, which is that like humans have all kinds of cognitive biases. And I think we don't have like much hope of engineering humans without these cognitive biases. But we do have hope of engineering machines without these cognitive biases.
Thank you. Is there a way to go to find out the pluses and minuses of the various LLMs across Claude, Chat, Perplexity, Grok, et cetera, et cetera?
Interesting. There are many, many leaderboards. Do you have a favorite? What was the question? The question was where to go to find out the pluses and minuses of the various LLMs and the different service providers.
You should come to our benchmark, live bench.
Let's go.
But there are benchmarks or like collections of benchmarks that test many different skills. It could be math skills, coding skills, different types of coding skills, different types of math skills, different types of reasoning skills, different types of knowledge questions. And you can just read off like, how the rankings change across different benchmarks. And like, for example, historically, the Claude models have focused highly on usability. They're much easier to coax good behavior out of, and this makes them really useful for coding. But it's not always reflected in the benchmarks. But so if you have like instruction following benchmarks and benchmarks that reflect like human written prompts for coding, Claude exceeds the performance of many other models. So there are lots of benchmarks for testing these things out. You just have to look at a lot of them.
And how do I access your benchmark?
livebench dot something AI maybe.
Livebench.ai or something else.
Thank you. Thank you for that something.
Yeah, so I had a question about the first talk. You mentioned how we don't want the policy to be iteration aware in labyrinth solving, and you said that you can just inject like random epochs in between them, iterations. And I was wondering if it's like that good of a solution, because if you end up being in a good solution, you'll kind of reward all the math you did along the way. So if it's a bit problem and like if it is, how would you mitigate it?
Yeah, so that's a good question. We tried some other ways of mitigating this sort of like iteration-specific behavior without removing the supervision from certain iterations, without the detach that happened there, just by training, for example, for random numbers of iterations or with some meta-learning approaches as well. And we found that it actually is a little bit worse. So I guess when you do the detach there, when you do some number of iterations, you detach from the computation graph, you decrease the computational cost. And so you could actually just train longer or train on more data. And it seems that you'll just always win that way by saving the compute with the detach and then training on more data or for longer. And you end up supervising your parameters just as much, despite not doing it as much on every iteration, because you just get to do more training.
Thanks.
Hi, thank you for both talks, actually, very interesting. So I don't know if anybody said that, but it was very nice. I have one tiny question to each of you. My first question is to the first talk. At the beginning, so you talked about how like small batches was very good for language models. Do you have any insights on how it works on other types of data? So for example, images in my case?
Yeah, great question. So the question is like, do the results there transfer to other things instead of just language model training? We've done some little experiments with images and it transfers there as well. The problem is that like for classical image classification training, for example, it's just very stable. So it's easy to train with small batch sizes, even with bad hyperparameters. Like if you do a bad job of setting your hyperparameters, it's still okay. Language model training is just an example where the loss landscape is particularly nasty and you really need a good optimizer to do it. But I think like that training different transformers is very similar once you hit a certain scale.
Okay, thank you. I'll show you nasty image database because I have some. But on the second talk, I have one small question on how, you know, you passed from GPT-3 to ChatGPT with your small like modifications, and how does that relate to what we imagine was actually implemented, or maybe for you, what is implemented now in like Gemini, because you might know more about that. Thank you.
Yeah, first I should say to camera, the rules that we provided do not fill the whole gap between the kinds of behaviors that GPT-3 made and the kinds of behaviors that ChatGPT made. They fill a surprising amount of the gap, surprising to us at least. And what do we think was the real change between them? Well, in my Comms 4705 class, we learned all about this. No, kind of two core things seem to have been changed. And I will speak no words as to what happens at Gemini, but what we think happened back a couple years ago to go to ChatGPT was first what is called instruction tuning. So the models were trained on a bunch of documents, a bunch of web documents, basically. And so if you give them some stuff, like a question, it assumes that it's sort of the beginning of a document. And so what can follow a question in a document? Maybe another question. So that's sort of the base model behavior. And then the instruction following model behavior, you just train the model further on, 1,000 or 10,000 examples of questions and good responses. And now the model, does quite a good job of following those instructions. It generalizes quite well. That was the surprising aspect, was the generalizability to all kinds of new questions that it wasn't trained on in those 10,000 because of that first pre-training step. And then the third thing that seems to be really important is that that instruction-tuned model is further adapted to try to increase the probability of the kinds of responses that humans particularly like. So now we're saying, I don't even know how to generate a human's favorite response here, but they said this one was better than that one. So I'm going to tell the model to generate stuff that's more like the one they preferred and less like the one that they dispreferred. And so those are the sort of real stages. So a lot of complexity in there, a lot of gradient steps. And that's what seems to have gone on between the models.
This is another question for John over here. What are some of the future implications of the third adventure that you talked about? Is it just to show that these models are adapting to our new vocab, or is it that they're, I guess, like generalizing to new stuff that is emerging from humans?
What's the implications of this work? I mean, in my dreams for this work are that there are all kinds of concepts that the models have learned about the world that we actually don't even know about yet necessarily. So an example of this that's inspired a lot of people is this famous move 37 in the AlphaGo versus Lee Sedol Go match, where human commentators saw this move that AlphaGo made that they thought was just fascinating and that no human would make. And only with a lot of analysis did it become clear why it was sort of a great move, is my understanding. I'm not a Go player. If we could label that concept of why the model made that kind of move in that kind of position, and if our language models sort of become good at Go, for example, I want to be able to have a new word for that thing we don't understand and actually learn all about why it's happening. So that's what I see for the future of that work. It'll actually help us to converse with and understand better these concepts that we don't yet understand about the systems we're building. The question is, how close are we understanding them? Quite far. Lots of research to be done. Seriously, quite far.
Hey, thank you for the talk here. I have a question about the first talk about the half-life of the atom's second momentum. So we see that the results are very, very good. So fixing the half-life is better than fixing beta 2. Do you have any intuition on why is that the case? Or how do you come up with this kind of idea?
Yeah, so as you decrease your batch size, essentially you're taking a step on way less data, right? So each optimizer step will depend on way less data, but your gradients therefore are getting a much noisier estimate of the like full batch gradient, right? And so the idea is like, how do I train with a small batch size and still update my model's parameters, like take the optimizer step using a lot of data? I had a small batch size, but using a lot of data. And the way is just to decay those moments slower, right? The optimizer step only depends on those moments. It doesn't depend directly on the gradients. So if I decay the moments very slowly, then in effect, I'm taking an optimizer step on a lot of data, even though the batch size is small. So you can think about this as some like relaxation of gradient accumulation.
Hi. You mentioned somewhere that the algorithm changes according to the training data, if I'm not mistaken. And I assume that makes it kind of difficult to know what the algorithm that is being used. So for the average user, non-expert, what is the state of the art to understand whether that LLM is providing accurate information back to that user when the user is not an expert? Is there a way to measure that? Is there a way for that person to know whether that information is accurate as possible with whatever state of the art of the technology is nowadays?
This is a question. So I guess this is a question for me, I assume.
Both of you.
Okay.
Yes.
So I guess like the way that we were determining what algorithm was running under the hood is just not a thing you can do in general for like, say, a language model. And I think that like, there are a bunch of startup companies right now that work heavily on trying to map the predictions made like by a language model back to, say, some data in some database. So you can think about this as like forcing models to cite their sources. I think right now this is like one of the big strategies for like how do you verify that what a model says is true. But I mean, what verification looks like is going to depend heavily on the application. In like mathematics, you might not be just like looking up in a table of facts, right? So like in mathematics, we have, for example, formal mathematical languages where you can just run a proof and see if it's correct, or we have like other sort of ways for informal math. So this depends on the application, but largely trying to tie model predictions back to some fact that we can look up.
I agree.
Thank you. Oh, hi. Thank you for the talk. Just like, I'll make this quick. I have a follow-up question for Micah in terms of like the difference between training in vision, training on vision text and like in text. Do you have like intuition on like why the loss landscape is like much messier in vision compared to text? For example, like I've seen like, it seems like if like it's okay to like train on data for like multiple like epochs for in vision, but like duplication is like bad in text. So I was wondering like if you have intuition like why is like harder, like why the loss landscape's like more much messier in text. So that like if we understand like why is that the case, then like maybe we can like use the text data better. If we know that like.
Yeah, this is a good question. So I actually don't think that the text setting is that different from the vision setting. And I think actually duplication is a very different problem than doing multi-epoch training. So it's actually not so uncommon, I've been told, in some frontier lab settings of doing a few epochs on text, because eventually, as you add more, if you're going to train on tons and tons of data, eventually using worse data. And so it's like, should you do more like, a couple passes on your highest quality data, or like, use that compute instead to train on junk data? And I think the duplication problem is like a problem of orders of magnitude difference than epochs here. It's like, if you think about all the websites that have all the different languages or countries sorted alphabetically, this occurs a lot. And so this is why we deduplicate our data. You'd have like tons of like occurrences of like copyright 2023 in your data set. This would be like, maybe 50% of your data set would just be boilerplate text like this. And it's important to deduplicate. But actually, like if you look at, for example, like the FineWeb paper or papers that look at deduplication, if you do too much deduplication, it can actually hurt in language training. So it's some of the reasons, like some things occur a lot because they're important, right? And so actually it's okay to train on the same thing, multiple times in text. And I think that the difference is really just a problem of availability. Like we just don't have as much really clean vision data as we have text data. And so like, if our biggest vision data sets are like in the like billions of samples, like single digit billions of samples, it's just less data. And so we epoch on them. Also, the models tend to be smaller. So vision models don't seem to scale as well as language models, which is maybe a totally different property here. And so because our models are smaller, it takes less time to train them per sample, like per, forward pass through the model, and therefore we can train on more data. So it's just, yeah, I think it's like more of a data availability and model size thing than like fundamental differences of like the loss surface and the optimization landscape.
With that, we'll thank the speakers and thank you all for attending. Thank you.